Hello, I'm Bruce. I'm your lab instructor for ENG 2151 Electronics. My email address, bmeisner@lakeheadu.ca. My website, electricallabs.lakeheadu.ca. On the website, if you go through year 2 and then ENG 2151, you'll have a lab manual there. That is a reference for you for helping you do your write-up. But what you're responsible for your lab reports, will be what's presented on the board today, and that's what you're responsible for to do your write-up for. Okay, so the first lab is, the content will be Ohm's law, Kirchhoff's voltage law. Okay, so the first circuit we do Okay, this is our first circuit. So it's a simple series circuit. It has two resistances. One is 330 ohms. The other one, we don't know. Okay, we will be using a 12-volt supply to power this circuit. Okay, so we start with Ohm's law. Okay, so we know from a series circuit that the sum of the voltage drops will equal the supply voltage. So if this is 9 volts, we know this is 3 volts. Okay, and so we can figure out the current by simply plugging in those values. 3 equals I times 330 ohms. Okay, and so I is going to equal 3 over 330, which equals 9.08 milliamps. Okay, so that's our total current. So we know now that there's 9 volts across here, and there's 9.08 milliamps flowing through it. So we should be able to calculate our resistance required here. Okay, so we'll continue on. R2 is going to equal 9 volts over 9.08 milliamps, which equals 990 ohms. Okay, so now what we're going to do is we're going to so now what we're going to do is build our circuit and test it. Okay, so if you would like to ask me for a 330 ohm resistor, I can give you one. But if you want me to give you a 990 ohm resistance, there's no such thing. Okay, so what we need to do is, there's a couple things we need. We could put 330 ohms in series, but that's going to be messy, right? The other thing we can do is simply use a 1 kilo ohm resistance. And that's probably going to be good enough, because here's what we're going to see. Okay, so what we have is our resistor. And our resistor has 4 bands of color on it. Okay, the first 3 are going to give you the value of the resistance, and the last one is what we call the tolerance, and I'll talk about that in a second. So the first 2 colors are straight up number values for resistance. Okay, so let's say, for example, our resistance is brown, black, and red. Okay? So brown, okay. The color code, I'll have to write that down. Okay, so every color denotes a number, okay? So if we are dealing with brown, black, red, that's going to be 1 and then 0. Okay, so the first two are number values. The third number or color is the multiplier, okay? So what we're going to have is 10 times 10 to the 2, which is the red. Okay, so it's 1, 0, brown, black, times 10 to the 2, which equals 1,000 ohms, or 1 kilo. Okay? And then when I do the demonstration of this, I'm going to use the 1 kilo ohm resistance, and it is going to be almost spot on what we want. Okay? Okay, so that's circuit number 1. Okay, circuit number 2. Okay, so circuit number 2 is still a series resistor circuit. One of the things we're going to see in this, our 1K resistance here looks a little different. And that's because this is a potentiometer. Okay, the potentiometer is something that can be used as a variable resistance or something to divide voltage as we actually, this little wiper, what we call, can be moved up and down by turning a knob on the potentiometer. And that changes the resistance, okay? So normally what I say, this is your 1K, this is A, B, and C terminals, so there's going to be 3 terminals. And I'll show you this when I do the demonstration. There's 3 terminals, okay? And as we dial this up and down, it will change the amount of resistance here because our voltmeter here, we're going to want it to measure 7 volts eventually, okay? But our voltage here is measured across RBC plus 100, right? So it's this portion of the potentiometer plus the 100 ohms. And that's what this voltage is going to be measured across. Okay? So when we hook up this circuit, there's 2 things that we want to do. We want to, 3 things. We're going to measure the maximum voltage this can handle, put out, the minimum voltage, and our 7 volts. Okay? So what we're going to say here is our V max is going to equal 12 volts times, now RBC, when it's the maximum, is going to be 1,000 ohms because this will come all the way up here, and so we're going to be measuring Okay, so it's going to be measured across the 1100 ohms here, and we divide that by the total, right? So this is Kirchhoff's voltage law. And what this is really saying here is that the total current in your series circuit is always the same. And we could say 12 volts over 1430 is the total current. We can also say V maximum over 1100 ohms is also the same, it's the same current measurement, right? And so that's what Kirchhoff does, right? He's just taken this ratio, mixed it around a bit, and it comes up with your, the same voltage ratio gives you this, we can calculate for the Vmax. Okay, so I'm going to let you calculate your Vmax. I will measure it for you later. Vmin is going to be 12 times 100 over 1430. So that's your Vmin. Okay? And then what we're going to do is measure it for the 7 volts. Okay? So for the 7 volts, we don't know what RBC is going to be, so we need to calculate that. So we can say, again, we can just plug this into our Kirchhoff equation. We could say 7 equals 12 times RBC plus 100 over 1430. Right? And then we can just solve for that. Okay? So we can rearrange this equation here, right? So we can say RBC equals, well, I can just subtract off the 100 afterwards, right? Is going to be equal to 7 times 1430 over 12 minus 100. And you can calculate the resistance that RBC is going to be. And then what we're going to do when we hook up our circuit, we're going to make the maximum and minimum measurements. We will measure for the 7 volts here. And then what we'll do, and I'll show you how to do this, is measure the resistance of RBC. Okay? And there's a little bit of a trick for that. So again, it's just understanding the instrumentation and what we're going to do when we do our demonstration. And I will elaborate a little more on that later. Okay, circuit number 3. Okay, this is circuit number 3. So in this situation, we have a couple of changes. We're going to be measuring the current. Okay, now measuring current can be catastrophic for your circuit. Normally, I don't want you to really do that. Because we can measure the voltage across a component and calculate for the current. Okay, and that's a safer way of doing it, because your voltmeter, when you measure with your voltmeter, the voltmeter is like a super high resistance. Okay? Because when you put a voltmeter across something, you don't want this resistance of the voltmeter to change the overall circuit characteristics. So this is almost an open circuit. In the case of an ammeter, the current needs to flow through the ammeter. So the ammeter needs to be very close to zero resistance. which means this can make it a short circuit condition if you put the ammeter in incorrectly. Because say if I was to measure the total current and we put the ammeter across our power supply like that, we just shorted out our power supply and we caused some damage. Blowing a fuse would be the minimum. So we don't want to do that. And that's why on your multimeters, you will have a separate connection for current, and then a separate connection for your voltage, because they have to be two different, they're basically two different devices. Okay, so here we go. We have our ammeter in our circuit. The other difference with this is that we have our potentiometer. We have A, B, and then C is left open. So in this situation here, we're using it as a variable resistor. Okay? So A and B are the only connections we're using on the potentiometer. Okay? So and again, we want to calculate for the I min and the I maximum. So I maximum is going to equal 12 divided by 430. So it's these two, and then so B is going to be all the way down here because the current, like with the voltage, this would be V minimum. But with the current, it's the maximum because now when the resistance is the smallest, the current is the highest. Right? So the current and the resistance are inversely proportional. As the current or the resistance goes up, the current comes down. And that's because the 12 volts is a constant 12. Okay? So that's I max. I min. Will be this. And then for this situation, we're going to dial it for 20 milliamps. Okay, so we can say 20 milliamps equals 12 divided by 430 plus R, A, B. Okay, and so this is going to be R, A, B is going to equal 12 over 20 milliamps minus 430. Okay? And then again, when we do our demonstration, we will measure these and you'll see that it's going to be right on. Okay? And now for the fourth circuit. Okay, so now we have a little more complicated circuit. We have resistors in series, but we also have them in parallel. Okay, and this is what we call a Wheatstone bridge. Okay, and this is very common. So, you know, if you're in a civil engineering or mechanical, you might be using a strain gauge. You would use a bridge circuit like this to actually put your strain gauge in because it's a variable resistance, and have it measure a voltage, and you would calibrate that voltage as far as stress or strain. Okay, so let's just take a pretty simple example. Okay, So all of our 4 resistances are 330 ohms. Okay? So, and this is 12 volts again. All right? So what we're going to have is on a parallel branch, there's 12 volts across each one of these. And then in the series branch here, the voltage gets divided. So if we were to measure the voltage from this point to the ground, we would have 6 volts. If we measure from here to the ground, we would have 6 volts. Okay? So when we measure from in between these 2 points, well, the other term for voltage is also called potential difference. And it's the difference in potential between these 2 points. So when we measure the voltage here, in this case, we would measure 0 volts. And we would say that the bridge is balanced. Okay? So let's take another example. Let's make these 660 ohms. Okay? So that would make the voltage at this point 2/3, right? Because this is 2, and then and this would be 3/3, right? So 2/3 of 12, okay, which is 8 volts, and then this is 8 volts. Okay, so again, we still measure 0 volts. Okay, the bridge is still balanced. But if we were to put back our 330 ohm, this would be 6, we would measure 2 volts. Okay? So, and then the bridge would not be balanced. So what we want to do, we're going to use our 330 ohm resistors on the top. I'm going to give an unknown resistance here. And over here, we're going to use a decade box, and I'll show you that in the demonstration. And the decade box, what it's going to look like, it's going to have dials on it, and basically you can adjust the resistance, hundreds, tens, ones, and 0.1 ohms of resistance. So we can dial this similarly to a potentiometer, but when we dial it, we can actually read the resistance right off of it. Okay? So that's what it's going to be. So I'll have an unknown resistance. You're going to have this decade box. And when we dial this decade box, we dial it till we get 0 volts. And when we have 0 volts, that means our decade is going to be the same resistance as our unknown resistance. And so we'll be able to determine what our unknown resistance was based on what we have our setting on our decade box. Okay? So that concludes the 4 circuits that we're going to do. Okay? So the other thing I should talk about is the lab reports. Okay? So the lab report, I want to see a title page, an introduction, the apparatus that we use, okay? And again, I'll go through that when we do our demonstration. Then I'd like to see, and there's multiple ways I'll accept this. What I like to see is circuit number 1, a description of circuit number 1, and your calculated versus measured results. Then you do circuit number 2. Do the diagram, right? Description, calculated versus measured results. And do it for the other 3. And then you can do a conclusion. And that's my preference for how you write up the lab reports. Okay? So This lab will take place in week number 2, and the report will be submitted to my email in PDF format within a week after the lab. Okay? So by the end of week 3, lab 1 will be submitted. Okay? So that's all I have for lab number 1 for 2151. There will be 5 different labs. I'll go through each one similarly in the other labs that we do. And after the labs, you will have, again, a written submission of a lab report. And again, email it to me within a week after when you do your lab, okay? Okay, so thank you, and I'll go now to set up the demonstration part of the lab. Okay, so here we are ready to do the demonstration portion of the lab. Hopefully you can see everything that I'm doing here. I've got my multimeter. We're going to set it to volts. The power supply is just right here. You can't really see it, but we're going to take there's a 12-volt terminal, and we'll bring it to one of these binding posts. And there's a ground terminal, and we will take it to another of the binding posts. Okay, so now if you recall our first circuit, we had a 330 ohm resistor. Okay, and what we do is we put the resistor in between 2 of the terminals. Okay. And we have our 1K resistor, which I forgot to get. We'll put that in between 2 of the other posts. And these just kind of clamp in between the posts. We will make a connection in between here, and we're going to use our multimeter to measure our voltage across our 1 kilo ohm resistor. And if you remember, it's supposed to be 9 volts. And what we have is 8.92 volts. Oh, and the other thing I guess I forgot to tell you about is the 4th color on the resistor is the tolerance, and it's a gold color. So it's plus and minus 5%. So again, that's the beauty of electronic labs, right? It is pretty close is good enough, right? If you're bang on the value, I figure you cheated, right? So this is a good demonstration where, again, there are some tolerances in the resistances. So a value of 8.92 is a pretty good symbol that this circuit is working correctly. If you need more precision, you can get better components, but then of course your costs go up. Okay, so for circuit number 2, right, we'll remove our voltmeter. We need our 330 ohm resistor. And now this is our potentiometer that I was talking about, right? So it's got the 3 terminals. Okay, so we're going to connect the 330 to 1. This 1 kilo ohm resistor we don't use. We need the one, this is a 100 ohm resistor here. Okay, and we'll make this connection to here and to here. Okay, and then when we measure our voltage, right, we're measuring from the ground to the wiper of the potentiometer, right? So this is RBC. This is RBC plus the 100 ohms, and that's what we're measuring across. So when we dial our potentiometer right to the bottom. So 0.8 volts, that's our V minimum. We dial it all the way up. 9.21 volts, that's our maximum. And then what we wanted to do, right, is set this for 7 volts and then measure our RBC and make sure it's close to the value we calculated for RBC in our introduction there. Okay, so here we go, we're dialing this for, and this can be a little touchy. We're going to get it as close as we can. Like actually that is pretty close right there. Okay, so now what we have to do is measure the resistance. And like I say, this can be a little tricky because one of the things, I can't just switch this to resistance and have it read the proper resistance. Because what the ohm meter does is it puts out a very small current and measures the voltage drop. And then it calibrates that in resistance, and that's how you measure it. So right now we have current flowing in our circuit. Plus we have all these other resistances in parallel with what we want to measure. It's going to throw off our resistance reading. So what we need to do is remove this from the circuit. Okay, so we're removing this from the circuit. Now this red lead can stay here. This black lead needs to come over to where this, so this is RBC, and then we dial this to resistance. And let's get it on a decent setting here. Okay, and it's 0.77 kiloohms. Okay, so 770 ohms. And when we calculated it out, again, that's a little bit off, but it's still not bad. Because one of the things, this is actually the 4th potentiometer I had to use. Because what a potentiometer is, it's a little graphite ring that has the certain resistance. So that's the 1K in between here and here. But the wiper is this little metal tab that goes across the top that's dividing the resistance into 2 different parts. And that can get built up with a little bit of a dust from wearing off of the carbon ring, and it builds up a little extra resistance. So these things, when they're new out of the box, they work really well. I mean, the other thing where you might see this is, or maybe more hear it, is if you have an amplifier at home and it's an older one and you turn the knob and it crackles, that's dirt and dust in the potentiometer and it's sitting on that wiper. And as you're moving it along, it's changing the resistance values drastically and it's not giving you the reading it should. And that's where you get the crackle. You got to clean your potentiometers. And you can only clean them so much before you have to replace them. Okay, so there we go. That's our circuit number 2. So circuit number 3 now, what we want to do is we put it for the, we're going to measure milliamps. Okay, I think I got to have it here. Okay, so now again, for this circuit, we need to come directly from the power supply, and sorry you can't really see this, but I'm taking the positive terminal of the ammeter and I'm putting it right to the 12 volt supply. And the negative of the ammeter goes to the circuit. So it's coming out of the supply into the ammeter, out of the ammeter to the 12 or to the 330 ohm resistance. Okay, and now we're going to put this on point A. This goes on point B. Right? And okay, and that should be good. And I'm not getting any current reading. Well, I'm getting a very, this is not good enough. So there's probably a fuse inside my ammeter that's blown. I should have tested it before I did this. It's toast. Okay. Okay, so what I'll do is I'll use my electronic one. I won't be able to show you the readings. But I will read them out. Okay. Oh, okay. Okay. So now in circuit number 3, right, what we're doing is we're going to dial this all the way to the here. So, okay, so our maximum current, so it's dialed all the way one way, is 27.24 milliamps. So 27.24 milliamps. And if we dial it all the way down to the minimum, it's 8.14 milliamps. Okay, so that's your maximum and minimum currents. And then for the, we're going to set this for the 20 milliamps. And again, I'm trying to get it as close as possible. Again, it's with these things, it gets glitchy because it's a little bit dirty, right? Okay. And so now what I want to do is measure this resistance here. And we should have calculated that out, right? And do this. And we'll switch this to resistance. And again, I'll just use this other meter here. And, no, sorry, I used the wrong cable. No, I want this cable here. And it is 159.5 ohms. Okay? And I think that's pretty close to what we should have been measuring. Okay, so now what we're going to do is we're going to get rid of the potentiometer now. Okay, now this is our decade box. And what we're going to do, we're going to start with everything at the maximum resistance. Okay, and now we're going to build our circuit. So what we need to do is we're going to take two 330 ohm resistors. Right? And we're going to put these in parallel. So we're going to join the two tops together. Okay. Now let's say, for example, let's use our unknown resistor as the 100 ohm resistor. Okay, and we'll connect the bottom of this to the bottom of this guy. And then the bottom of this resistor goes to the top of this one. Okay, so we're going to switch this now to voltage. So I'm going to put this in between these 2 points here and here. Okay, we're going to put our plus 12 on the top here and our ground on the bottom. Okay, so right now we're getting a value of 1.12 volts. Now this voltage could be positive or negative depending on how you hook up your circuit, but that's really irrelevant. But now what we do is we start at the maximum resistance and we start dialing it down. And you can see how this is actually going up, which it shouldn't be doing. Oh, I forgot a connection here. Yes, I need to connect these two together. Okay, so now we have a voltage of negative 2.67. But we'll see now this should decrease when I start changing this, right? So I'm dialing this down more and more and more. And what I want to do is dial it all the way down until the sign changes. And it actually, okay, so actually the 100 ohm resistor is kind of a bad example, because now this is basically 100 ohms here, and you're basically at 0. So here, let's just do this. Let's go back. I'll get a different resistor.